are for the third of the Year 12 mechanisms. Nucleophilic. In the context of Year 12, this means reactions of halogenoalkanes. Some books refer to them as haloalkanes. I have to say I struggle with that. It's been halogenoalkanes all my life. So in the context of what we're going to do, it's going to be those. You do get them with alcohols as well, but we're not going to do that. 4, but there are more halogen forms, halide ions that are nucleophiles, but not in the context of halogenoalkanes, which is why it's not here. Those are 2 fully negatively charged anions. Here are ones with a partial negative that we use. The mechanism for these has an additional step compared to the more straightforward mechanism for the hydroxide and the cyanide. Halogenoalkanes, you need to know the difference between primary, secondary and tertiary. Secondary is a sore point because of the way it doesn't do one thing. I'll tell you about that in just a second. Just make sure you know what primary, secondary and tertiary halogenoalkanes are. So if you were to look at the carbon chain and find the bromine attached to the carbon on the end, that carbon is only attached to one carbon, primary. If you were to look at a carbon chain where the bromine is there, it is now in the 2 position, that carbon is attached to 2 carbons, secondary. There's only 1 hydrogen here. Here there are 2 hydrogens, but it's better to, in terms of the number, I think, to go how many carbons. Here's the halogen attached to the carbon. How many other carbons are attached to where the carbon is, where my finger is? And here it's 1, here it's 2. So when you have tertiary, that there, you would find a carbon situation, something like that, or you could have an extra carbon over there, it doesn't really matter. And yeah, one there as well. Why not? And therefore that carbon is now attached to 1, 2, 3. That makes it tertiary. Now the irritation is secondary. I'll do that in just a second. Primary, which I have to say, A-level wise, if it's going to be a question about mechanisms and it's going to be nucleophilic and it's going to be substitutions, it's going to almost always, I can't even think of a question when it was secondary, it's always either going to be primary or tertiary. Now the mechanism for primary and the mechanism for tertiary are not the same. You need to know that because you need to know the 2 mechanisms and you need to not get them confused and you need to not conflate the 2. So primary, tertiary, got to have the 2 mechanisms. Irritation with secondary is it does a proportion of this mechanism and a proportion of this mechanism, resulting in 2 mechanisms taking place, and it's just annoying. So you don't see a question that says what will the mechanism be for a secondary. I think the only thing you need to know is it does the mechanism for this and the mechanism for that. Unequal proportions, I would suggest. Now I need to clean the board, and I've been having trouble cleaning the board because I need to get kitchen spray out. So we'll take a little pause whilst I get the board ready for the next bit of this video. See you in a moment. Here we are with what we're going to do with primary. Now I've written up there Sn2. Most of the time in A-level courses Sn2 doesn't get a mention until year 13 when you do rate of reaction. But it always links back to halogenoalkane substitutions. So what's the harm in introducing it early? Get used to it, and therefore you know it's coming. Sn2, what that refers to is S for substitution, N for nucleophilic, and 2 because there are 2 species, one's the nucleophile, the other one's the organic, involved in, well, it is kind of the starting step, but that's not the right way to think of it. It's really involved in who controls the rate of how fast this takes place. And both of them are involved, so it's Sn2. You'll do more of that when you do orders of reaction in year 13. However, the name is Sn2. And it applies to primary. I've said already, like before we had the little board wiping edit, that secondary does it, but secondary also does the other mechanism, which is coming up after this one. Now, you look at this, I've got it on the board twice. Why have I got it on the board twice? Because there's the straightforward mechanism where hydroxide ion. Now I've written hydroxide ion backwards. Why have I done it backwards? Because the oxygen carries the negative, not the hydrogen. And what happens is, when you look at this way, the charge is distributed around this molecule here, which is 1-bromopropane, so therefore it's primary. Bromine, delta negative, makes the carbon delta plus, and electronegativities indicate that that will be the case. So the negative on the OH will be going, be inexorably drawn towards the attractiveness of the delta plus. So it will go in there and that will get kicked out. But one of the things you're asked to do is, what's the sort of, it's called a transition state, what's the halfway sort of position? Because it is like a gradual, I'm coming in and you're leaving, it's a thing. So you get this, and you tend to draw weaker bonds longer, which is why that looks a bit more like, like that. And so the OH, got enough room for the OH, there we are. So it looks like that. Now the whole thing actually carries a charge. Why does it carry a charge? The 1-bromopropane has no charge, but the OH does carry a charge, so the whole thing carries a negative charge. And the whole thing continues the gradual in and out, and eventually you end up with, now some people don't like these three-dimensional drawings. Well, I think you're going to have to get used to them, because it's part of the A-level tenet is that you have to be able to do these things. So there it is. Oh dear, that's a terrible hydrogen. No, not much better, but there we are. So you get an alcohol, in this case propan-1-ol, as the product. Now the reason this is here is not that we're doing the same thing again. I'm not. If you wanted to do this and you wanted to do that with a different whole charge nucleophile, the mechanism is identical. The cyanide ion carries a negative on the carbon, and the result would be, those would be changed for carbon joined, nitrogen on the end, carbon, nitrogen. Oh dear, that looks terrible, can't read it, let's try and rub in harder. Carbon has got a triple bond there, so you would get, these are termed a nitrile, and that's a propane nitrile at the end there. So the mechanism is identical when you have a whole charged nucleophile. So if you have another whole charged nucleophile that you've never met before, the mechanism would be the same. The reason I've got this here is when you've got an uncharged nucleophile that's got an electronegative atom in it, an example would be ammonia. Delta negative on the nitrogen, same polarised bond in the 1-bromopropane. The whole thing is the same. You get the same intermediate state. But what the subtle difference is that when you have that there, the bromide has left carrying a negative charge. So being as ammonia is uncharged, 1-bromopropane is uncharged, when the bromide leaves, it leaves a plus charge. Why have I done it on the nitrogen? Because the nitrogen's got the wrong number of bonds. Nitrogen has 3 bonds, currently it's got 4. That's where the bonding mismatch has taken place. What then happens is NH3 comes round picks up one of the hydrogens, becomes NH4 plus. You've still got the Br minus, and you've then got a product of an amine. Now, in some courses, you go on to do, oh well, this can then go on and substitute onto the 1-bromopropane a second time, and you get multiple substitutions. But not all courses do that, so I'm going to leave that bit out because this makes the video too long. So you get ammonium bromide and you get an amine. Now, if you did that with water, the process is the same. That goes on as delta minus H, and you end up with oxygen, which should have 2 bonds with 3. Another water comes along, plucks off the hydrogen and leaves you with an alcohol as the product, where the water has removed that, all of that is gone, plus charge vanishes, and you're left with an alcohol. I need to clean the board for the tertiary version, so I'll see you very shortly. So, did SN2. Here is what is termed SN1. S and N stand for the same thing. The 1 refers to the fact that the process is controlled by only one chemical in terms of rate. So I've got it again on a split pair of mechanisms, only because nucleophiles carrying a whole negative charge mechanism is simpler, but not massively simpler than ones where you use a molecule. Water is my example this time, where you have to remove a proton, remove a hydrogen. So, driven in this mechanism is the fact that 3 alkyl groups. Now, one of the things that alkyl groups do in molecules is they push electrons towards other things. So what happens here is methyl groups push electrons. Now, ethyl groups are better at this than methyl groups, and propyl groups are marginally better than ethyl groups. They push electrons towards that central carbon, and what that does is what would normally be decided by the difference in electronegativity between carbon, in this case bromine, gets accentuated, and it pushes electrons down that bond that way, weakening the bond to the point where it's very easy for the bromine to leave on its own accord. So we're going to do the reaction with the hydroxide ion, but the hydroxide ion isn't involved at the beginning in what determines how fast this takes place. That term is called rate determining step. So what happens is this weakened carbon halogen bond becomes a carbocation all of its own accord. It is to do with being in the environment of being in an alkali, because otherwise it would just do it naturally. Now, there are some tertiary, because this is tertiary, that actually do that. There's a dye that does it called crystal violet that has it's so stable that this ion being crystal violet stays intact permanently. So the bromide has left as Br minus because that bond has done that. That means that this is a carbocation because the bromine is left with its one extra electron that wasn't its in the first place. Then, and only then, does the OH minus go in and form the alcohol as a product. If you were to do this in water, now water, it's not really water. Really, almost all times you see water doing this, it's in silver nitrate solution. That's just the way you do it. You do it with silver nitrate solution. But the process is the same. The bromide departs, so termed a leaving group. The carbocation is the same as the previous one, so there's commonality there. Yeah, there's commonality between the Sn2 mechanism as well. And then lone pair on the oxygen goes and forms a bond. What you have then is the same kind of situation as before, where the oxygen has one too many bonds. It's come in onto a positive ion. The oxygen now carries the positive, and then another water comes along and plucks off the hydrogen, leaving you with, in the end, the same product as that one. You could do that with ammonia, and you get ammonia plucking off one of the hydrogens to make the amine. Not necessary to know that they're called Sn2 and Sn1. I just think it's knowledge that you're eventually going to have. It seems to me sensible to at least know the names. What you do need to know is how the tertiary mechanism is completely different in terms of how it gets started to the primary mechanism. And like I said, secondary mechanism is a mixture of the two, so the secondary offloads sometimes and does the shuffle in and out at the same time than the other ones. But you don't get asked about secondary, at least no one can remember when it was last asked. So there we have the Sn1 mechanism, which only applies to tertiary. Now tertiary halogenoalkanes, because we're focusing on halogenoalkanes, there aren't that many to choose from because they've got to have carbon attached in 3 places around the central carbon. A lot of the time, in fact the majority of halogenoalkanes are secondary, which is annoying because you can't ask questions about them. But there we are. Thank you very much for listening. There is some questions to go with this for you to practice on, and then there'll be a follow-up video rather than me type up the answers, which will take me about a week because it's so awkward doing arrow pushing answers. I will do a video with the answers to the questions. So I look forward to seeing you for the answers. So there's been 3 of these videos. Thank you for watching them. I hope they've been helpful. See you soon. Bye bye.